Routers use an IP version 4 address on each and every interface. In this video, I'll show you how to configure those along with some other important interface settings. Let's go. As always, if you're using the book, this content matches content you'll find in the Volume 1 Cert Guide, Part 5, Chapter 16 in the current edition. And in that chapter, we've got two major sections. A different video covers the content you'd find in that first major section, installing Cisco routers, and this video is about enabling IPv4 on those router interfaces. In particular, in this video, I'll cover those topics in this order. I'll talk about configuring those IP version 4 addresses, and then how to check the interface status, because for the interface to forward and receive IPv4 traffic, it needs that IP address and the interface has to be up and working. Then two ancillary topics, some settings related to Ethernet interface auto-negotiation, and then for all interface types, this idea of interface bandwidth. As always, stick around to the end and I'll give you advice about what to do at the end of the video, where to focus your studies. I'll point you to a lab exercise that has some videos associated with it here at the channel, and then how to best use that book content. All right, let's get into it. Let's talk about interface IP addresses with an example. We'll use this topology with 4 different routers, and I've shown the LAN switches, but the LAN switches really aren't part of the discussion. And there's some PCs, but I'm focusing on router interfaces and router interface IP addresses. So we'll look at the interface IDs that I see here, and they could have been any router interface IDs. I just picked some for reference. And then I created an IP addressing plan and picked some addresses that you see here in this table. Now, all the thought process that goes into picking those addresses, we covered in the previous part of the book and of the video course, all right? In fact, part 4 ended with a big exercise where you could go through the process of planning and figuring out IP addresses like these, all right? So I'm not going over that again. You're at the point where you've planned the IP addresses, you've got a table like this, and you just need to implement them in the configuration of routers, like, hey, how do I get that IP address and mask configured in the router? Well, that's the next step. To configure those IP addresses, all you have to do is get into config mode, get into interface config mode, and then configure the IP address. Here's how it goes. There's you getting into configuration mode on router R10. Then the interface command moves you into interface mode for one of the interfaces, and then the IP address command configures the address. It's literally IP space address, then the dotted decimal IP address, followed by the dotted decimal mask, and that configures the IP address. Do the same on another interface, IP address with that different IP address and its mask, and those commands configure the IP address. Independent from that, you can use that no shutdown command that we talked about in an earlier video. Now, no shutdown administratively enables the interface. It's a very oddly named command, most people think when you first learn about it. But the shutdown command disables the interface or shuts it down, and no shutdown brings it back up again. So let's just say when you set about to do the configuration on this page, both of these interfaces were in a shutdown configuration state. So with the first one, we issued the no shutdown to bring it up, and the second one, maybe we didn't use that no shutdown command, we forgot, all right? So that's where we are at the end of this example. So next, if we did some show commands to check the status, and we started with show interfaces gig 01 up at the top, well, we get a lot of lines of output, and it wouldn't fit all on the page, so I'm just showing a couple of the lines. The first line would be this one, then a few lines, then this one, and then some more lines. That's what the 3 dots here are for. But that first line shows the interface ID, and it gives the first of 2 interface status codes, and then line protocol is, and the second of the 2 interface status codes. Now, because you issued a no shutdown to bring it up, and everything's physically working on that interface, then the 2 status codes are up and up. That interface is working. And we see the IP address we just configured on gig 01, and we see the prefix style mask, not the dotted decimal mask that we just configured in that command. So once again, it's important to be good at mentally converting between the styles of masks, just so you're comfortable with that kind of thing. Now on the other interface, we still see the IP address we configured on gig 010 in that case. But notice the interface state is, quote, administratively down in the first status code. Now, what does that mean? Anytime you see administratively down, it means there's a shutdown command configured on the interface, all right? Then the line protocol is also down. It means we forgot to issue that no shutdown command. Now, if you just wanted to see the IP address and those interface status codes, you could use show IP interface brief, and it would give you one line per interface. And here are the two that we've been focusing on in this example. We see their IP addresses. Notice it doesn't show the mask, just the IP addresses, and we see their status and protocol status. So the line status and protocol status in this case. So just to be complete, if you wanted to enable that second interface, you get back into configuration mode, get into interface config mode for gig 010, and issue that no shutdown command that will administratively enable that interface. Then just to make sure you've seen an example of it, there's a third command you might want to use commonly to figure out what's the interface status and what's the IP address. It's show protocols. Show protocols gives you a couple of lines of output per interface when it's configured. For instance, on gig 00, it tells you the line is up, the line protocol is up like before. It gives you the IP address and the mask. Show IP interface brief doesn't show the mask. Show protocols does show the mask. All right, so that's the advantage there. And here's gig 010, again with the IP address and the mask. And now it shows up instead of administratively down. By the way, this video is sponsored by me and my books. If you don't happen to have them yet, and you click that link or scan the QR code and go to my link tree and click the products link there and buy the books there, you don't have to spend any more money, but those sellers happen to give me a few dollars back from the sale. It's a great way to say thanks and support the channel, and I'd very much appreciate it. All right, back to the content. So let's talk about those interface status codes as an end to itself for a moment. As a reminder, we started out that demo with one of the interfaces in an up state. That is, the line status, the first status code was up, and the line protocol status is up. Whereas the other one, we had a shutdown command configured, and anytime you've got a shutdown command configured, the line status is administratively down, and the line protocol then is just shown as down. All right. Then you can see those with show IP interface brief. It's one line per, and you see the status codes there at the far right. Now, what causes those different status codes? Well, we talked about this to a fair amount of depth on switches, and it's the same general rules, but there are some subtle differences on routers. So let's talk about things on routers, and specifically with Ethernet interfaces, because those are the most common interface types you're going to see on routers, definitely in the context of what's covered for CCNA. So you're going to see these two-word status codes on routers. On switches, some commands show an alternate one-word status code. You don't see those on routers, all right? So the router interfaces two-word status codes. And so that's the line status, that's the first code, and the protocol status, that's the second one. And you'll just hear people talk about it in shorthand like up, and down, and things like that, all right? And here are the common combinations, and I'm going to talk you through that set of combinations with some scenarios. So the first case is when you see an up, that is line status up, line protocol status is up. And here I've got a router with a short cable over to a LAN switch in the same rack, so it's the router's LAN Ethernet interface. And whenever you see up, it tells you things like this. There's a working cable connected at both ends. If it's copper cable, a UTP pinout, it means we're getting electricity over the wires. The pinouts are correct, or they're incorrect, and the switch has made up for the incorrect pinouts with auto MDICs. If it's fiber, we've got the correct swapping of transmit to receive on each fiber. And both interfaces are enabled. That is, neither end has a shutdown command on it. So that's the good case. That's where we want to be. Now, if you see an admin down on either end on the router or the attached device, that just means that device that's in an admin down state has a shutdown command. If the shutdown command is configured, it overrides any other logic. It doesn't have to check the cable. It's just administratively down. Next up, let's say you did some kind of a show command and you see there's a down state. Line status is down, line protocol status is down. For instance, here on the router in a down state. This covers pretty much everything that points to any of the possible physical issues on the link. All right, so there are a lot of root causes when you see a down. It could be something as simple as no cable is installed. It's installed, but it's broken. I've seen people do this where they go inside the cable and clip a couple of wires just to show an example of a broken cable. Maybe you plugged it in before and someone came along and unplugged it. It could be on Ethernet cables you've configured to where it can only use one speed and you use different speeds on opposite ends of the cable. You've used the wrong cable pinouts for a UTP cable and the switch is not correcting for that with auto MDIX. If it's fiber, you've got transmit connected to transmit, receive connected to receive. That won't work. So anything you can imagine that could go wrong with the physical installation of the cable will lead to a down state, assuming you've got no shutdown configured. Once again, if you've got shutdown configured, you'll land in an admin down state there. All right, one more case to go over. It is possible for an interface to land in a line protocol. Sure, line is up, line protocol is down, so an up-down state. But honestly, on the Ethernet type interfaces you're going to see in CCNA, it's really not expected to see an up-down state. In the old days, when you would see more serial interfaces in CCNA, those actually had some common cases that would land you in an up-down state. But those are back in the historical past. Today, you might see an up-down state on a router interface with what I would call layered links. Those are cases where you take one protocol and run it over another protocol, and that's real in the world. It's just not something that's brought up as early as the CCNA certification. So I would say don't discount it for your career long term, but for worrying about CCNA, don't worry about seeing any up-down states crop up. So to summarize here, administratively down, you've got a shutdown command configured. Down, that's the catch everything cabling problems. Up, down is unlikely. Up, all good. Interface is useful. Ethernet auto negotiation. Isn't that about switches? Well, it's about anything with an Ethernet interface. So let's talk about it in the context of routers for a moment. Say you've got this router with a short link to a LAN switch. The router is going to use auto negotiation, the switch will too, and they'll decide to use the best standard that both support. So they'll have this link, they'll come up. So when the interfaces come up to initialize, they'll send these Ethernet fast link pulses. Those contain messages. The messages are for auto negotiation, and they'll each state their best speeds, all their speeds they support, all the duplexes they support. Both ends do that, and then together they each decide, I'll use the fastest speed and the best duplex, which in this case would be 1 gigabit per second, full duplex. Use that. That's normal. Use the default setting to use auto negotiation. Cisco documentation says use auto negotiation. It works great. That's what you want to do in real life. What we have to be ready for CCNA is the fact that, yeah, you could make poor choices and turn off auto negotiation on one end, say down here at switch 2, then the router has to deal with that, or vice versa. All right, so you have flexibility with the commands and you can make choices that aren't so good. So let's just say in this case, switch 2 turned off auto negotiation down here. R1's expecting those fast link pulses so it can do auto negotiation. The switch, however, instead of sending those fast link pulses, sends data using the standard it was configured to use. Let's just say it was configured to use 100 meg Ethernet, so it sends frames at 100 meg. What happens? Well, per IEEE auto negotiation rules, R1 has a backup plan, and that backup plan says, hey, notice that that frame that's arriving, it's not fast link pulses, it's just a normal frame, is using a standard defined by the 100 meg standard. So I'm going to recognize that incoming encoding as 100 meg and use that speed as well. Then I have to choose a duplex, and I'm going to use this table of defaults. If I happen to see that incoming encoding as 100 meg, then I'm going to choose to use half duplex. So that'll be the combination that R1 figures out with this set of rules. All right. But because it's having to assume what duplex to use, that's what creates this potential for a poor choice, and you can end up with issues like duplex mismatches. Now, I'm not going to get into the details of the issues about this duplex mismatch. It's covered very well in the earlier auto negotiation topic that's focused on switches. But I do want to tell you about is how to configure router auto negotiation settings so that you can avoid creating this duplex mismatch, all right? To do that, you have to think about router operating systems. So here's a bit of a tangent. Once upon a time, there were routers and there was one operating system for them. It was called iOS. And that's today used on older models of routers. You'll still bump into it. But for routers used inside enterprises, companies, not service providers, but the companies that connect to the internet, we call those enterprises. Those use an operating system that's a newer, better type of operating system called iOS XE. All right, so newer models use that. So what's newer and better? Well, the old iOS was one big piece of code and it ran that piece of code, but it wasn't modern in terms of being separate processes. It worked well with a multi-processor CPU chip. Whereas iOS XE was modular, it made for better software development. It worked better with a multi-processor CPU. So it's a single process with iOS. It's multi-process with iOS XE. It's got a Linux kernel. Linux manages the process switching and managing the processes inside the operating system. So a much more robust, easier to update, easier to develop operating system with iOS XE. Now, most of those things you and I, as people that buy routers and deploy them, don't have to think about. What matters to us in that discussion is that some commands differ, not many, but some commands differ between iOS and iOS XE. The command line interface, it acts the same. It's still configure terminal to get into config mode. It's still copy run start to save your config. But it turns out the Ethernet auto negotiation commands differ comparing iOS to iOS XE. All right. They don't differ a lot, but they do differ. So here we go. iOS, the older operating system. There's no command specific to auto negotiation, but there's a speed and duplex interface subcommand for Ethernet interfaces. The defaults are speed, auto, duplex auto, which means use auto negotiation for each of those settings. Now you can override those. You could set the speed and leave the duplex on auto, leave the speed on auto, and set the duplex explicitly. And if you do that, either of these combinations, setting one but not the other, it leaves auto negotiation on, sending fast link pulses. It just locks you in to one or the other setting. So leaves Ethernet auto negotiation on, but locks you into one setting. But if you configure both speed and duplex, then it disables auto negotiation, setting both of these. Now you've opened up to the possibility where if the other end's expecting auto negotiation, it could cause a duplex mismatch, which is bad. All right. But in real life, use auto negotiation. All right. I'm just covering the bases so you're ready for the exam should they ask something on this particular topic. So that's iOS, the older operating system. iOS XE configures a little differently. So the defaults, speed auto, duplex auto, along with this command unique to iOS XE, negotiation auto, and this one explicitly says we're using auto negotiation. Now you can reconfigure, but to reconfigure, if you want to set speed to a particular number or duplex to full or half, you must first use this command, no, negotiation auto. That command disables auto negotiation. Basically, XE won't let you set the speed or duplex until you turn off auto negotiation. So at this point, it's literally off, whether you change the speed or duplex or not. Again, opening up the possibility where if the device on the other end of the link is relying on auto negotiation, then guess what? You've opened up the possibility of creating a duplex mismatch. All right. So the configuration is a little different. Then for show commands. So what's there? Well, you can always do a show running config and see what's configured, right? So that's the best way to know what's intended. But if you want to see the speed in duplex, if you use show interfaces on iOS, you'll see the speed and you'll see the duplex that's actually being used. But nothing in the output tells you whether it found that using auto negotiation or not. So iOS doesn't tell you whether it used auto negotiation. iOS XE does, but it's hard to find, right? So it tells us the duplex, it tells us the speed, tells us the duplex, tells us the speed. But what I've got here are two different interfaces, the first of which used auto negotiation, and the second of which used configuration having turned off auto negotiation. Notice this phrase, link type is force up, explicitly configured auto negotiation off, whereas the earlier one, link type is auto. That's pointing to the fact that auto negotiation is used in that case. We'll wrap up with one short topic on interface bandwidth for routers. So all routers have an interface bandwidth setting. It represents the link speed. In fact, it can be set to the exact same speed as the physical link speed, and it's normal to do that. So normally this value bandwidth will match the physical link speed, but it does not have to match it. In fact, just for fun, I checked on a router and found that I could set that router from a value of 1 to 200 terabits worth of bandwidth. Even on an interface that could at most run 1 gigabit per second. All right, so point is, it's a software setting that's independent from what's happening physically on the interface. And it may be useful in some cases to change it to something different from the physical interface speed. So what's this software setting meant for? Well, it's used by interface statistics, it's used by quality of service tools, it's used by routing protocol metric calculations. So it could be that you want to use the same number that represents the speed used by the physical interface, and it could be in some cases that you want to use a different number, all right? You've got flexibility. What's used normally? Well, because in CCNA, most of our router interfaces are Ethernet, whether it's for LAN or for WAN. Let's take a look at what happens. By default, if you don't configure the bandwidth will match the physical interface speed. But the bandwidth is in kilobits per second as a unit. So if you do a show interfaces command, the bandwidth's on the fourth line here. It says BW for bandwidth, and that's a 1 million, 1,000,000, if they added the commas in there. So that's 1 million kilobits per second, and you can't change the unit. So 1 million kilobits is the same as 1 gigabit or 1,000 megabits. All right, so this is a reminder that, hey, the link is running 1,000 megabits, and there it is in the output of the show command, 1,000 megabits. Now, if we were to change the configuration on this interface to where it was running 100 megabits, and we had not configured the bandwidth setting, then the router would automatically change the bandwidth setting. In fact, I did just that. I went in and configured the speed to 100 megabits. If you look closely, now the bandwidth is 100,000 kilobits, which is equal to 100 megabits. All right. So normal circumstances, Ethernet interface, the bandwidth tracks to the physical interface speed. Now you can configure the bandwidth to any value that's within the range on that particular model of router. In this case, I've done that on this interface gig 00. I got into config mode, typed the bandwidth command, and I gave it a number. You don't type kbps for the units, you just type in the number, but the unit is kilobits per second. So if I repeat the show interfaces command, and I look at the bandwidth setting now, it says bandwidth is 1234. The unit reminder here is kilobits per second, so 1,234 kilobits is the same as 1,234,000 bits per second. But the physical link speed is unchanged. The bandwidth command has no impact on the physical encoding rate on the physical interface. That's just what the software uses to calculate interface statistics and perform QoS features and the like. So where do you go from here, study group? Well, we're here in the closing section in chapter 16. It's all about IP version 4. But granted, there are a lot of small topics in this video, right? So number one is how to configure those IP addresses. You should practice those in the upcoming lab. I'd say the number two out of what I've just talked with you about is what causes those down-down interface states. Go through all the list of failure reasons. It all has to do with physical failures on the link. Lab. I'm pointing it to a lab. It's Config Lab 117 on my blog site, and I've got a series of config labs there about configuring IP version 4 addresses. I picked lab number 2 in that series. It uses this network diagram where you've got 4 routers that are connected to a central subnet, and each of those 4 routers have an outer subnet, as you see on the top and the bottom here. The diagram shows the subnets. The lab exercise shows the specific IP addresses and directs you how to choose those. You can do this one in Cisco Packet Tracer or CML free, as it turns out. So you can go to that link and do the lab. It's also got Config Lab intro and review videos as well. In the book, it's always great to grab the book section and read it as a second source. I'd give it a few days and maybe do the lab first, and then give it a few days and use the book section to review that as well. Next up is an instructional video on IP routing, the core of how a router thinks. Click on the left to get to that video. But if you're ready to do that lab first, click over on the right and you'll get to the Config Lab intro video for that lab. I'll see you there in the next one.